Good evening to our Australasian attendees and good morning to those of you joining us from the UK and Europe. My name is Tor Lund. I am the Secretary of Friends of Holbrook Submarine Museum and the convener of this webinar. Before I introduce the panel, there are some things I'd like to talk about as we go forward. Firstly, the tragic loss of the San Juan in South American waters, and more recently, the loss of the Indonesian submarine KRI Nanggala, have sparked interest in rescue and submarine accident survivability capabilities in our region. The panel tonight will discuss some issues associated with those, but essentially they'll be in the modern context of what we do here in Australia. But before we launch into the webinar, there are a couple of accidents that I think are worth noting that do set somewhat of a scene for both rescue and escape. Firstly, the HMS Thetis accident happened after the inner hatch on the torpedo tube was opened while the outer hatch to the sea was also opened. Tragic mistake and also some issues mechanically that needed to be solved, obviously. 4 men successfully used the submarine's one-man escape chamber before a fifth panicked and jammed it. A total of 99 men lost their lives as a result. Tragic accident. On the other side of the Atlantic, the USS Squalus sank off the coast of New Hampshire during test dives on the 23rd of May 1939. Sinking drowned 26 crew members, but an ensuing rescue operation using the McCann rescue chamber for the first time saved the lives of the remaining 33 aboard. There are definitely lessons learned from these early tragedies that will be discussed in light of our own attempts of rescue and capabilities here in Australia. But it is worth noting that we do learn from the past. And without going into them too much further, I'd like to introduce you to the panel for tonight, which is a 4-man panel. Starting with Frank, he was the Secretary of the Submarine Institute of Australia, and he served over 30 years in the Royal Australian Navy, specialising in submarines. In 1996, Frank was responsible for the introduction of a sovereign submarine escape and rescue capability, with a similar capability later adopted by the USN. Frank's comments were much sought after following the tragic Nanggala loss recently, and he's always an authority to get hold of if you can to find out what is happening. The second member of our panel tonight is Peter Horrobin. Peter is a former submarine commander and commanded HMAS Otway in the 70s. He was the director responsible for the James Fisher Global Submarine Escape, Rescue and Abandonment operations, which included the NATO submarine rescue system based in Faslane. Third member of our panel tonight will be well known to some of you. It is Toff Idris. Toff is a former submarine engineer who has served on a number of the REN's Oberon class submarines. Toff was recently the managing director of JFD Australia and who was the current provider of submarine rescue systems to the RAN. And last but certainly by no means least is Brad Smith. Brad has been involved in the offshore oil and gas industry as a diver for some years, but more interestingly for tonight's episodes, he was a tank top supervisor and training officer responsible for pressurised escape training for Australian and international submariners. Brad has also been involved in all Black Carillion exercises since 2013 and has conducted live escapes from a Collins-class submarine. So with this panel all in place now, I'll hand over to Frank to head off proceedings.
The system differently, and several either died or suffered severe decompression sickness. The loss of the Russian Oscar-class submarine Kursk grabbed the attention of the world in August 2000, when a torpedo malfunction resulted in sympathetic detonation of the submarine's own torpedoes. Sinking in 130 meters of water, which was beyond the capabilities of the Russian escape system, attempts by the Russians to rescue the 23 survivors who were aft of the reactor were unsuccessful. And although the British mobilized their rescue system, the Russians refused to allow it to be launched. The only other rescue system that could have been deployed to the Barents Sea, Australia's Remora, was also ready for deployment, but the government decided not to offer assistance. Norwegian divers were eventually allowed to inspect the escape tower, and you can see that grainy screenshot from the television there, and managed to open it, but discovered that the compartment was already flooded through water that had leaked past the shaft seals. A good outcome of the accident was a recognition that submarine accidents required rapid and trusted communications, leading to the formation of the International Submarine Escape and Rescue Liaison Office, known by its acronym of ISMERLO, initially based in Norfolk, Virginia, and now in Northwood in the UK. It was that trust that developed as a result of ISMERLO that led the Russians to call for assistance only 5 years later, when one of their own rescue vehicles, I've clicked and this hasn't gone, I better get two now, that when one of their own rescue vehicles, the AS-28 Priz, became tangled in cables associated with seabed hydrophones that it was being used to inspect outside of Berezovaya Bay on Kamchatka Peninsula, and didn't think I'd get through that without stumbling. Within 12 hours, the call for assistance was made through ISMERLO, and response teams flew in from both the UK and the US. Ultimately, it was the Brits who were chosen by the Russians to clear the cables, and the Priz surfaced 72 hours after the alarm with almost no breathable air remaining. Fast forward 12 years, and ISMERLO became involved again when the Argentinian type TR-1700 submarine, the ARA San Juan, reported difficulties in heavy weather and then sank. You can see the propeller is one item in that middle photograph that was taken by Ocean Infinity when they did find it. On this occasion, rescue forces, including the US Navy's pressurized rescue module Falcon, were unable to locate the submarine, and it would be several months before the wreck was found, having collapsed in over 900 meters of water. Finally, the litany of disasters continued even to this year, when the Indonesian Type 209 class submarine KRA Nanggala was lost with all crew plus 15 trainees and plus 4 senior squadron staff in 840 meters of water north of Bali. The cause of that accident is still not publicly available. So there's some lessons out of all of this. The submarine might have sunk, but it may well be the figurative frying pan, and the surface may be the fire should surface forces not be in place to assist. Whether escape or rescue is the end result, it's vital that the environment inside the submarine is properly managed. The key factors, hopefully within the control of the survivors, will be air quality, being oxygen and carbon dioxide. The other factors that will influence the choice for escape and rescue, of course, are pressure and temperature. Whatever the scenario, the response will take time to be brought together for the location, intervention, recovery, and ultimately rescue. And finally, it's also of note that rescue vehicles are designed to rescue, but as a result, I beg your pardon, as a rule, they're not search assets. I'd like to hand over now to Peter Horrobin, because all those lessons that we've learned through experience from tragedies, Peter will weave together a story of how early tragedies led to major change in submarine escape. Thanks, Peter.
Thank you very much, Frank. I'm delighted to talk to you, ladies and gentlemen. Thank you for your interest in this important subject. At the end of the Second World War, the British Royal Navy commissioned a review of submarine losses led by Captain and later Vice Admiral Philip Ruck Keane to investigate submarine escape. The findings in his report led to many of the practices submariners use today.
They're also a reminder that if we fail to learn the lessons of the past, we're very likely to repeat the tragedy. The Ruck-Keene Committee reviewed 26 submarine losses, from which 172 people attempted to escape, of whom 84 were successful. Many people were killed because they either stayed in the boat too long and hence were overcome by noxious gases. They did not follow the correct procedure during their escape, such as not operating the escape tower correctly or holding their breath during their ascent. Ruck-Keene emphasised throughout the report, the people in the sunken submarine are very cold, very frightened, numb, and incapable of thought. Some of his quotations are worth recording. Men must be regarded as quite incapable of doing anything but the simplest of tasks. Note that at that time, women were not at sea in submarines. In Thetis, for example, when using the forward chamber as an airlock, flooding up was stopped on 3 occasions because those in the chamber disliked the discomfort of going under pressure. Ruck-Keene reminds us it's better to burst a man's eardrums and get him up alive than to delay the escape. And sadly, in the case of Thetis also, one of the escapees attempted to change the exit procedure and effectively blocked the tower. And in so doing, that caused the death of the other 99 people. Training and proper instruction is one of the major factors in successful escape. Disasters and mistakes are most entirely due to ignorance of simple physiological facts and a lack of knowledge of how to use the equipment. The survivors in a submarine can be expected to be in a dazed condition, incapable of cooperating to the full or of carrying out anything but the most simple drill. The Admiralty accepted Ruck-Keene's recommendations and established the training procedures we see today. The single most important recommendation was that the training for submarine escape be as near as possible to the real experience. I'd like to hand over to Brad Smith now and ask Brad whether his experience training today's submariners has followed some of these principles.
Thank you very much, Peter. As you've mentioned, one of the recommendations of the Ruck-Keene report was the establishment of a specialised facility to train submariners in the techniques of submarine escape and surface survival. The embodiment of this concept was the construction and commissioning of HMS Dolphin. This bespoke training centre was the model adopted by a number of nations to deliver pressurised submarine escape training, or PSET. The PSET model was unique, with in-water instructors utilising breath hold techniques in the delivery of training, to the trainees themselves conducting both head in water and head in air rapid buoyant ascents from pressurised compartments within the water column. The course was structured around trainees completing a final 30-metre ascent from the single escape tower, followed by surface survival techniques on successfully reaching the surface. Those familiar with diving physics and physiology will recognise any rapid buoyant ascent from a pressurised compartment, no matter what the depth, presents a significant risk to all involved. The health and safety of service personnel is paramount, and with the majority of nations looking for an alternative to PSET delivery, we have seen a shift to unpressurised submarine escape training. Arguably, PSET still represents the best mechanism available to familiarise submariners not only in the process of a set escape, but more importantly, in providing crews the confidence to conduct a real-time escape from a disabled submarine. Not to mention one of the best and most rewarding jobs I've ever had. The shift to unpressurised submarine escape training now provides not only a safer training environment, but increases the knowledge and skill sets of submariners by providing additional, we can run back one, please, Tor. By providing additional training modules relating not only to escape, but also rescue. The unpressurised model now covers in detail surface abandonment, using the Submarine escape suit with attached single seat life raft, and also multi-person life rafts incorporating casual. All of the above practical modules, plus the theoretical components of unpressurised training, combine to provide crews with a detailed and complete understanding of escape and rescue. The recently commissioned Submarine Escape, Rescue, Abandonment and Survival Facility at Her Majesty's Naval Base Clyde represents the most modern unpressurised training facility to date. The potential for future development of escape training will undoubtedly see the increased use of virtual reality systems to better simulate training scenarios and further reduce training risk to personnel. The image in this slide is of the US Navy's Project Blue Shark. The project's virtual reality technology is being used to simulate vessel operations and combat scenarios, providing operators with a 3D view of their environment. It's not too much of a stretch to envision a program that would allow crew members to conduct simulations relating to preparations for rescue or tunnel and tower checks pre-escape. There also exists the prospect of escape and rescue theory components delivered as a self-paced online course during crew workup periods. An advantage to this style of training would see whole crew familiarisation of escape and rescue systems annually or as required, rather than only during requalification periods, typically every 3 years. While those from the old school may have reservations towards this style of training, we need to be cognizant that the next generation of submariners are already very familiar and accepting of this technology, not to mention the submarines they will eventually crew will be greatly enhanced with similar systems and technology. I'm reminded of a tour that I took a couple of years back on the Virginia-class boat USS Texas. While in the CIC, I asked the young submariner where the periscopes were, only to be shown 2 high-definition screens and a PlayStation controller. The ability of a submarine crew to identify and immediately respond to a potential incident, coupled with an extensive scheduled and preventative maintenance program, greatly reduced the likelihood of a potential dis-sub event. However, at some stage, I'm sure we've all experienced Murphy's Law, and that anything that can go wrong will go wrong, and the ability of a submarine crew to improvise and adapt to a situation not specifically trained for is not to be underestimated. The history of submarine escape has shown the majority of such were not conventional, in the sense that the crew were either unable to access the tunnel and set, or functionality of these systems was compromised. In fact, a number of factors must align to ensure a successful rescue or escape from a dis-sub. By and large, any crew preparing for rescue or conducting set unmanned runs is having a very bad day indeed. I'll briefly identify 2 examples that I've used during delivery of escape training to reinforce this point before handing back over to Frank. First is the USS Tang that unfortunately sank herself due to a torpedo malfunction in 1944 and the actions of torpedoman Hayes' truck. His story of survival and the odds faced to achieve a successful escape are extraordinary. Relying on the knowledge, skills and confidence gained at the US Navy Submarine School in New London, he conducted the first heading water ascent from a depth of 180 feet after losing his Momsen lung on leaving the escape trunk. This method of escape had never been attempted before from an American submarine. Finally, an example highlighting the importance of system knowledge in sinking of the British E-class submarine E41 following a collision with her sister boat, the E4, in 1916. The actions of Stoker Petty Officer Brown to conduct an improvised escape from the engine room of E41 became legendary in the British First World War submarine fleet. With the engine room hatch only 5 feet below the surface, P.O. Brown, relying on his thorough knowledge of the complex gearing mechanism securing the inward opening hatch, was able to overcome several securing devices, allowing water into the compartment at a steady rate. Eventually equalising with the outside water pressure, he was able to force the hatch open against the securing springs and make his bid to the surface. I'd be happy to provide any additional information on the escapes from the Tang or E41, should anyone wish for greater detail. To our audience this evening, I thank you very much for your time. Frank, you have the con.
Right, thank you very much indeed, Brad. I'm going to talk a little bit about submarine rescue and where it started. And before we do that, we need to have a little understanding about that not all submarines are compatible with rescue systems. If we start with it, you see on the right hand side this little simulation of a submarine pressure hull with an extension that from through the hull, which is the escape tower. The gusseted seat around the top is called the rescue seat, and on the outside of that is the submarine fairing. And all of these are basically the same size because they have to allow the upper escape tower upper hatch to open inside the skirt. Now the skirt is fitted to a rescue vehicle, and this sits inside the circumference of the rescue seat. Once it's mated to this seat, the water inside is pumped out so that there's a differential of pressure. It's then either fully pumped to sea or drained inside the submarine, depending upon the rescue vehicle capabilities. Once it is now full of air and the pressure inside is equalized between the rescue vehicle and the submarine, the hatches open and the survivors transfer. So the original, one of the first systems designed was done so in response to lessons learnt, and it was a submarine rescue chamber, sometimes referred to as the McCann Bell. It really should bear the name of its real inventor, Swede Mommsen, later Vice Admiral Mommsen, who also discovered the reason for the US Navy's torpedo failures during the war, when he actually got a torpedo fired against a rock in Hawaii, then swam down himself to recover the failed exploder. Despite its age and its limitations, it remains a part of the US Navy submarine rescue flyaway kit. From the Thresher accident emerged the SubSafe program and the Deep Submergence Rescue program. Of the 5 deep submergent rescue vehicles planned, the budget only allowed for 2, Mystic and Avalon. These were very capable, very expensive, and they spawned 2 lookalikes in the Japanese Maritime Self-Defense Force. And you can see there how they were carried. They were piggybacked on the back of a US nuclear submarine. They spawned the Japanese deep submergence rescue vehicles, which are also capable, but in many ways are more capable because they're fully integrated with a complete transfer under pressure and hyperbaric treatment system in the 2 Japanese motherships, Toyota and Chihaya. They are, however, not air portable in the way that the US Navy's DSRV was. The next offspring of the DSRV was the free-swimming submarine rescue vehicle. It became available as the offshore oil and gas industry shifted to diving bells and remotely operated vehicles. And they're very capable and widely used, although they do carry a heavy training load. This is a drawing of LR5 currently used in Australia, and there's a recent image of LR5. Toff will talk a little bit more about that, so I won't dwell on it right now. When Australia took the decision to build its own submarines, the Navy started looking seriously at how it could deal with an accident. One of the first things it did, and I'm very pleased to see that he's in the audience, was commission Lieutenant Gus Mellon, as he was then, to do a study into the resources needed for a submarine emergency. And he produced the Subsunk Resource Study. And that became the template, or the writing instructions, if you like, or 5 of the recommendations were for a project that was then assigned to the submarine project, which was tasked with acquiring a capability for escape treatment, transfer under pressure, and rescue. And against a very demanding time frame, the project office acquired 2 36-man triple compartment recompression chambers, a transfer under pressure chamber, a rescue, and the world's first remotely operated rescue vehicle, known as Remora from the suckerfish that go on sharks, but less politely known as the really excellent method of rescuing Aussies. Remora later was fitted with its own launch and recovery system, and you can see there the cursor frame, which was fitted to the top, and this is Remora as it came out of the water, and you can see there the articulated skirt that allowed it to mate at 60 degrees. From Remora came the US Navy submarine rescue vehicle, the pressurized rescue module, now known as Falcon, named after the rescue ship that hosted the submarine rescue chamber Bell rescue of the USS Squalus. And they established the submarine rescue diving and recompression system. This is basically the same footprint and weight as Remora. It's about just under 20 tons, and it's in essence a 20-foot ISO container. It has its own articulated skirt with a 45-degree limit angle because they positioned it at the end of its purpose-built pressure vessel to allow for more survivors to fit in. It can embark 16 rescuees, and you can see there the similarities, the same launch and recovery system, and it's in service today. And the other, while we're on the subject of today, I'd now like to hand over to Toff to talk about Australian submarine rescue today. Toff.
Good evening. Thanks, Frank. Good evening and good morning to everybody. So Frank's taken us through what effectively is the evolution, if you like, of submarine rescue services and capabilities. What I'd like to do now, what we'd like to do over the next few minutes, and probably about 15 minutes or so, is really talk about what might a contemporary and modern submarine rescue capability and service look like. So I would like to declare first and foremost that I will be unapologetically borrowing quite heavily from my most recent appointment as the Managing Director of JFD Australia, which I had the privilege of holding for nearly 5.5 or just on 5.5 years. So with that, it will also be a conversation predominantly regarding submarine rescue capabilities and service from an Australian context. So let's see whether this will work. All right. So what are the ingredients of a contemporary submarine rescue capability today? Look, without a doubt, first and foremost, you need guidance and you need a roadmap. I think any organisation or country that is serious about employing and achieving a competent, reliable submarine rescue capability needs to first and foremost understand exactly not what's necessarily required, but how it's meant to operate. So there I show the front cover pictorial of a particular ADF unclassed publication. Its role really is to provide a number of things. It's a very good document from a procedural perspective in articulating the various phases of submarine operations, submarine rescue operations. It talks about command and control, which is absolutely critical in such a complex and multidisciplinary, multi-domain environment such as a submarine rescue. It also talks about the types of assets one might employ. It talks about timings and transportability. So all the critical factors that actually materializes and turns a theory into operations, takes concept of operations into reality, is the type of either doctrinal or procedural document that one needs to be able to prepare and then execute a capability that is dedicated towards submarine rescue. Secondly, you need an organisation and leadership. Now, in the context again of the Australian point of view, we're not talking about a single entity. Indeed, we're talking about an ability, a united capability that comes together in an organised fashion. So without a doubt, the operational client for any submarine and the operator for any submarine rescue operations is without a doubt the fleet commander and the submarine force commander as his specialist. In the Australian context, the actual service is provided through a contractor, such as JFD Australia, And so therefore, contractually, you also need a third party, which is the Capability and Acquisition Sustainment Group, that translates the operational requirement in order for the contractor to actually meet it and satisfy it from an operational perspective. So organisationally, it can be rather complex. And so therefore you need strong organisational rigour and also leadership to make sure it all comes together when you actually then deploy for operations. The third component is that operational capability itself. And here we are talking about people, but we're also talking about processes and procedures and the assets and the systems themselves. Without a doubt, and certainly from my very recent experience over the last 5.5 years, you cannot underestimate the vitality and the requirement for training. Submarine rescue operations, submarine rescue exercises are not insignificant in terms of their cost to the parent Navy and to the parent government. And so you need to embrace and hold with both arms every training opportunity that you are given. So training then isn't just an adjunct or an afterthought. It becomes an implicit part of that operational capability itself. And that goes through in all your documentation and also in your preparations. Last but by no means least, and again, this is probably not germane just to the Australian context, but more and more industry is becoming very smart in terms of providing and delivering services and capabilities to defence, whether it be here or overseas. No less is that the case in submarine rescue operations. So whether or not it's about the availability of a welder or specialist riggers, or in the case of one of the photos that I'm showing there, the availability of contracted commercial divers, which are there to specifically provide support to the launch and recovery of the submarine rescue vehicle or vessel, the submersible, we would not be able to deploy, we would not be able to be ready, and we would not be able to execute without that very long supply chain support base. The principle for all of those 4 nodes, if you like, cardinal nodes in terms of submarine rescue operation framework, is quite simple. When we're talking about a disabled submarine in rescuable waters, then the fundamental and underlying principle is all time. And it's time to be ready. This is not time to get ready. So the investment and the costs associated with being ready cannot be underestimated. If you're not prepared to invest so that you have a very regimented notice to move protocol in place, then really you are suboptimizing your rescue operations and capability. The time taken to the time taken to get to the disabled sub site, the time to first rescue and the time to last rescue, the endurability of your operations can be calculated and therefore becomes a very fundamental ingredient in the success or otherwise of your submarine rescue operations. So it is all about time. Okay. So from an Australian point of view and Australian context, the submarine rescue operations, the doctrine is really what I coined to be based on a 2-ship, 2-functional rescue concept. So the first ship is the escape gear ship, and it's all about intervention. And as the name suggests, this is about getting an asset to the disabled submarine location as quickly as humanly possible. Its mission is very, very clear, and that is to get to site, to affirm the location of the disabled submarine, and then to lend assistance should the submarine be able to actually successfully produce escapees. And there may be reasons why a submarine crew might initially be able to escape and then not be able to escape. So the requirement to therefore gather and extract the escapees from the water, be able to give them medical treatment, and potentially also, because they've come from depth, they've been exposed to pressure at depth, and therefore the ability to treat them hyperbarically. One of the key aspects about the intervention suite is actually, as Frank had mentioned previously when the pictorial about the rescue suite, the rescue seat, is to actually make sure that the site is clear, that the rescue seat is clear of debris. It's also there to assess and ascertain the attitude and the aspect of the submarine. Is it on a list, or is it actually on a bit of a heel? Has it got a bow up or bow down angle in terms of where it sits on the seabed? And most importantly, also, is just, you know, what is the environment like in terms of the tidal stream at depth, or whether or not there are actual hindrances to a successful rescue operation with respect to the water column itself above the disabled submarine. So these are the sorts of things the intervention in the escape gear ship is meant to achieve, and why we want to get to the disabled submarine site as quickly as possible in preparation for rescue. So the types of assets that might make up such an intervention suite, and again, you know, this reflects the Australian capability. Without a doubt, you wouldn't be able to conduct a rescue seat debris clearance operation without something like a remote operated vehicle. So that's one of the things that it does, and the ROV has manipulative capability, whether it be for line cutting or just, you know, the ability to hold and operate a variety of hydraulic tools. The ROV for the Australian suite is able to be operated at 1,500 metres, operated by a notional crew 24/7. And so it also provides the very much needed eyes on in preparation for the rescuers on the surface, in preparation for rescue. I also maintain that the ROV, you know, once rescue operations is underway, and while you need to be mutually separated, has the ability to also provide a level of capability in terms of a safety number for the actual rescue operations as being conducted by the submersible. Probably a most recent advent in the Australian system has been the portable side scan sonar. And not unlike the requirement and the mission of the ROV, again, it's another tool that provides a picture to the rescuers on the surface. And this picture, this sonar picture, is invaluable in terms of how the submarine is actually sitting, the aspect, the immediate topography of the seabed from a surveillance perspective. And again, just to give that situational awareness in terms of what's around the submarine and what might be around the submersible as it undergoes its actual rescue operations. And as you can see there, the actual picture, the sonar picture from the portable side scan sonar is absolutely incredible. It's impeccable, and as a tool for the rescuers on the surface, it is extremely implicit part now of rescue operations in the Australian context. I mentioned before the need to potentially hyperbarically treat escapees, those people that have been able to escape prior to rescue operations being conducted. So on the back of the intervention ship or the escape gear ship are these portable decompression, recompression chambers, the ability to accommodate up to about 14 with 14 built-in breathing masks, operate to around 5 bar and twin lock, so therefore allowing you to maintain the main chamber at depth while allowing you to go in and out and transfer medical equipment as need be. And of course, in both the escape gear ship and the rescue gear ship, there are what we call subsunk stores, and these are medical stores, a variety of medical equipment and also stores, but also general stores, and they may be stretchers, it may be drinking water, it may be food, it may be it may be blankets. So subsunk stores are also accommodated on the intervention suite in order to replenish if we are able to replenish the disabled submarine. I mentioned it's a two-ship, two-function rescue concept. So the second is the rescue gear ship. Its role is very clear, very black and white, and that is to proceed to the disabled submarine site as fast as possible and execute rescue. The three major roles, if you like, is to therefore proceed safely down to the disabled submarine, mate with it, and then transfer the crew safely to the surface. It is then meant to be able to provide medical treatment as required, and then provide hyperbaric treatment as required in terms of those submariners that may have been exposed to pressure while in the disabled submarine. So what does an RGS or the rescue suite comprise of? Without a doubt, the centerpiece, if you like, would be the rescue vehicle itself. One of the fundamental characteristics, and whether it be, and I should hasten to add, and I think Frank did touch on it, while the Australian rescue system and some others around the world have a free swimming submersible, there are others which are tethered. The principles of rescue, however, between them, how they mate, are largely similar. One of the characteristics of the submersible is the ability to actually have the submersible. It's made up of two structures or two compartments, if you will, and the front compartment is the actual command module where the first pilot and second pilot can operate at 1 atmosphere. Now, this is absolutely critical because the back end of the submersible, which is the chamber end, must equalise and therefore be at the disabled submarine pressure. It then must stay at that pressure until such time as it can mate with the hyperbaric suite on the surface. Throughout all of that, you don't want your first and second pilots and your crew to be exposed through a variety of pressures. They must be able to continue to operate at 1 atmosphere. And so the SRV is cleverly designed to allow them to do that. So three crew, a pilot, second pilot, and also a chamber operator. The LR5 in the Australian Submarine Rescue Suite is able to rescue 16 submariners at a time. So a standard Collins class submarine may be between 46 to 60 personnel. So you're looking at 4.5 to 5 sorties for a rescue of a disabled Collins class submarine. Able to mate up to 45 degrees. And again, that's critically important in terms of how the submarine's aspect might be on the seabed, and has an ability to fight a tidal stream at depth of up to about 2.3 knots. The jewel in the crown, though, from my perspective in the rescue capability, is the hyperbaric equipment suite. There is absolutely no point in being able to rescue submariners at depth if you are unable to therefore safely treat them and bring them back to the surface hyperbarically in a safe fashion. So in 2018, the Australian suite, the Australian system commissioned the current hyperbaric equipment suite, manufactured in the UK, fitted out in both Singapore and locally here in Australia. And it is a wonderful capability. It is a quantum leap in terms of what it can do. And it effectively, as I said before, it takes the submariner at depth and then safely transitions them to the surface through the use of diving profiles and what we call diving tables, which are rigorously supervised by the RAN medical team and specifically by the RAN medical doctors who are underwater qualified and specialists. Ability to house 88 personnel, and that's in addition to the staff. And so therefore you can quite easily see that in a single mission made up of multiple sorties, we are able to, or the Australian Navy is able to now treat a full Collins class submarine. Perhaps the poor cousin and unsung hero, in my view, is the simple crane, if you like, the launch and recovery system, highly hydraulic. And in the Australian system, it is perhaps the oldest launch and recovery system and portal handling system in the fleet of similar type equipment. It has a 36-ton lift capacity and capability. And again, it is crucial. Without it, the inability to therefore launch and recover the submersible becomes a major deficiency of the capability. And so a lot of tender loving care is given to this hydraulic beast in order to make sure that it continues to operate the way it's meant to at sea. And we do actually construct, JFD and the Australian Navy do construct this from time to time ashore to just put it through its paces. So very quickly, how does all this come together? So it is all about readiness. It's a program of processes, both from a material perspective and also a people point of view. And I note that Peter Huguenet is also in the audience. So hello, Peter, and I'm sure I hope you are well. But there is a subset of a program that Captain Huguenet was implicit in introducing into the RAN in the day, and that is the SubSafe program. So today, the SubSafe program has a sub-program within it, which is known as the Submarine Rescue Certificate. But in addition to that, a lot of expense is placed in terms of investing in a third-party classification society certification as well. So all this certification is meant to do one thing and one thing only, and that is to provide objective evidence and assurance that the submarine rescue capability is able to deploy when it's meant to deploy and within 12 hours notice to move. So a lot of investment. So first and foremost, if you want to be serious about submarine rescue, that it is about the investment in its readiness. In terms of its actual operation, I'll very quickly go through. Frank has already mentioned the International Submarine Escape and Rescue Liaison Office. So when an incident occurs, and this was very much the case in November 2017 with San Juan, and again with Nangala earlier this year, is that the alert phase is really made up of a bunch of things, not the least of which ISMERLA, but also open source media and also the submarine network. So the moment that a rescue capability or service gets wind of and is able to understand and be alerted to a potential disabled submarine incident, then a lot of things start to happen, including the preparation of the paperwork, the planning, and the alert phase of the people itself that will deliver and deploy the equipment. We will get called out, or they will get called out, and again, in the Australian context, that will most likely be a phone call from the headquarters Joint Operations Command in Bangalore to Navy, and Navy then in turn to the contractors and to the rest of the team. Interestingly, if it's a foreign submarine, then clearly we will be guided by the direction from the Government of Australia and the decisions at the time. In the case of San Juan, that never came, but we were prepared to deploy as required and to provide assistance if the Australian Commonwealth required it so. In the case of Nangala, I can say that we were asked to be ready with respect to certain elements of the intervention suite itself. Mobilisation is the longest pole in the tent, without a doubt. And this is now about both constructing and erecting and mobilising assets onto the back of both the escape gearship and the rescue gearship. One of the things that I would like to stress here is that while the mobilisation, that is the physical action of actually getting ready before you actually deploy, is a big part of rescue readiness and rescue operations, behind the scenes, a lot of work is also done in the planning and the intelligence associated with things like the vessels of opportunity, the intelligence behind suitable mother ports and also suitable airports. So again, it's not just about the movement of assets in order to get to the site and then execute rescue. It is about the pre-planning, and it is about the pre-planning for even the most mundane things, and that is the logistics and the engineering construction of the assets themselves. We then also start the rescue planning once there is an understanding of where the submarine is, confirmation, affirmation of the aspect, the environmentals, and we've got everyone's green light. And environmentals is absolutely crystal clear and is underpinned by some very stringent risk assessments and processes. And again, there is absolutely 0 point in conducting rescue operations if in doing so you're actually endangering and risking the rescue assets themselves. So there is a lot of effort in making sure the environments are right in order for us to actually go. Launch is then executed, and then it's just a process of the crew cycling through, mating of the submarine, transferring the submariners, and you can see the picture there. It's reasonably cramped in LR5. It's not a huge volume of space, but hopefully it's not a long trip either from the disabled submarine to the surface. And then we actually conduct the treatment, and the whole aim is to make sure that the submariners are able to walk out of the decompression lock of the recompression chamber on their own, breathing healthily, breathing well, and healthy in order for one thing and one thing only, and that is to go home to their loved ones. Once we've achieved that, then we then turn our minds to returning to base and reconstituting the assets. So we've gone through a fair bit there in terms of the assets and also the process. I hope that's been informative, and with that, I'll hand you back over to Peter. Thanks, Peter.
Thank you, Toff. So with the proliferation of submarine forces worldwide, and especially in our region, the importance of understanding and having access to a reliable, proven submarine rescue service is becoming increasingly part of any nation's maritime capability. Society's expectations demand an effective submarine escape and rescue capability. We are fortunate that our region is particularly well served. China, India, Japan, Malaysia, Singapore, South Korea, Vietnam, as well as Australia, have submarine rescue systems that are also able to support submarine escape. The majority of the submarine rescue systems in the region are fitted to their individual mother ships, known as a rescue gear ship. While the systems are very capable, they are constrained by speed and range of the vessel in which they're embarked. Australia, India, NATO, and the United States have an air transportable rescue system. They too have limitations in that there is a high level of complexity in their mobilization, transport to an embarkation port, and embarkation into a vessel of opportunity, as Toff has just explained. However, all of the air transportable systems are able to reach a sunken submarine within 3 to 4 days. While the International Submarine Escape and Rescue Liaison Office, which Frank and Toff have talked about, is a NATO entity, it supports all nations and pursues the involvement of global submarine operating nations. It operates in an international environment and is focused on the humanitarian objective of saving lives at sea. Through the efforts of Vice Merlo, most countries now use the NATO-agreed procedures to conduct submarine search and rescue. I've described here, and Toff's covered them very much better than I, the 3 phases in a search and rescue activity and the critical time calculations to rescue survivors. The faster one can locate the disabled submarine, the greater the chances of survival for its crew. The anti-submarine warfare forces are best able to do this, and the disabled submarine can help itself by launching communications devices and making noise to attract the searching units. Having located the disabled submarine, more detail of its status, as Toff has just explained, can be determined by examination using a remotely operated underwater vehicle, and in some cases, the resupply of stores to the submarine. Maintaining a high state of readiness 24 hours a day, 7 days a week, 365 days a year is an essential part of the business of submarine escape and rescue. The organisations must be ready to respond to call out at all times, and this readiness is tested frequently by the organisation itself, by the Navy, and in major exercises, both national and international. In major exercises, if there is a single lesson for me, it's that the submarine escape and rescue is complex and requires continuous and focused attention to detail. I'll hand over now to Frank Owen, who will sum up our presentation.
So in the last hour, we've had a very quick gallop through in many ways, everything to do with submarine disasters and the lessons and the ways in which people can recover from them. There's no doubt that a submarine disaster focuses the mind. The lessons that came out of all of the early submarine disasters have formed the basis of our escape system and the rescue systems that really started to emerge from the beginning of the First World War until now have moved in really quite big steps. Escape training has evolved, and the changes in escape training, and I will admit to being one of the hoary old ones who doesn't necessarily agree that pressurized escape training is a bad thing, but the fact that they have a good, safe escape training system now is great, and we only hope that the lessons of Ruck Keane, who said that you won't necessarily remember all your procedures, also are there. We've heard and seen that we have a very solid capability in Australia. We also, that's complemented by a lot of strength in the region. And each of them has strengths and weakness, but its collaboration and time are the key ingredients to see the successful conclusion to a submarine disaster. So I thank you very much for your attention from around the world. And for those of you who are on the east coast of Australia, it's getting to be late at night. You lot in UK, you're just getting up, so half your luck. But thank you very much for your time, and we're now ready to take any questions you may have that you can pose through the chat line, if you have any.
Frank, it's Tori. I have a question for the panel, if you can hear me there. Does the panel think that Australia has slipped in its standing within the world SMER community, noting one, we no longer do PSET, and two, there is a delay in bringing into service a replacement system to LR5 and HES? From Guy.
The short answer is no. Have we? If the question is, have we as an Australian nation slipped because of the fact that we're still running what some might argue to be an aged system, or that we've given up pressurised submarine escape tracing? I think the answer, certainly for mine, is no, we haven't. And why do I say that? I say that because it's not just about the assets themselves of, the assets of today or the assets of yesterday or the assets of tomorrow. It is largely also about the paradigm and also the framework that now supports all that. We've become a much more professional organisation. I think it would be safe to say, and it's probably brave of me to say it with this audience, but I think it would be safe to say that submarine escape and rescue these days, Frank and Peter and Brad, is probably a more professional sub-discipline to submarining than it has been in the past. And because of that, I think that professional development brings with it higher expectations. And it's not just amongst the submariners or industry, it's also amongst the non-submariners who are accountable and responsible for submarine escape and rescue. So I think for mine, the answer is the Australian nation and the Australian Navy has not slipped in terms of where we sit amongst others.
So I had another question, gentlemen. Brad indicated that pressurised escape training is still important. Is the RAN's ZF still in operation?
Thanks, Tor. Yes, it is. Currently, the RAN conduct unpressurised submarine escape training, and that model has again been borrowed from the UK's unpressurised training model, the basis of which is very robust, and initial feedbacks from the fleet are very positive. It is in its early stages, and I would anticipate further development as we receive more feedback from the fleet. But all in all, I believe the training remains world-class. And as Toff mentioned, the individuals that conduct the training have been in the facility for a long time, and that experience has definitely shown in the development of the unpressurised course.
Another question for the panel is on the loss of the Indonesian KRO Nanggala. China dispatched rescue resources. Does anyone have any comment on what was done? Because
I was talking a lot during the Nanggala, and this sort of question was asked of me by various media outlets. I didn't hold a lot of confidence that they were going to be able to lift the whole submarine. If you've only got to look at the lessons from the recovery of the Kursk and other, even though it was a bigger submarine, it's a significant commercial, heavy lift commercial activity. So the Chinese, I think, enhance the spirit of collaboration, cooperation, and probably have a good understanding of the environment of Indonesia's waters as well.
We've got time for just a couple more. This one is on Turkish submarine. On the 14th of July 1942, the Turkish submarine Atalay was sunk. Any crew at the 68-metre depth have been saved?
I'm not familiar with that particular accident and know not enough of it to answer that question, I'm afraid. Does any of the other panel have any information on it?
No, Frank, no.
We can take that one into our history books, and if
Take it on that. Yep.
answer, we'll get back to you on that one. I think one last question before we close up for the night is, from a rescue vessel, what time frame is available to transfer to a hyperbaric chamber?
Toph could answer that.
Yeah, so if the question is what sort of time frame are you looking at for a typical sortie, I guess the first answer is that it depends on how deep the submarine is at. So first and foremost, submarine rescue from a submarine Australian suite point of view, the submersible can go to 400 metres. The organisation has clearly operated close to 400 metres in terms of previous Black Carillion exercises. So roughly, it would take about, for memory, from launch to recovery back onto the back of the ship, anywhere between 2 to 2.5 hours for a particular sortie, depending on the environmentals and depending on how quickly you can actually get the mating done. And again, that's going to be dictated by currents and tidal streams and weather. But if all goes well, from between, I can personally recollect that going to about 150 metres for a rescue and then going back on the back of the ship again, you're well within a couple of hours of doing that. It then mates with the transfer under pressure chamber. It then so you then decant the submariners through that, and then again transfer them to the hyperbaric suite. The time taken to therefore get a submariner from that pressurized situation to 1 atmosphere and back to the surface is largely dictated by the pressure that they're exposed to when they're at depth. And again, I did mention that would be determined by the use of certain dive profiles and tables, which are rigorously employed by the RA and doctors. But largely speaking, I would say that, and again, there's people in the audience that are just as experienced or more experienced than I in terms of the operations. You are looking at probably a turnaround time of between 4 and 5 hours of sorties, depending on the depth. And that will also include the need to recharge, of course, LR5's batteries, which you do need to do, given the fact that there are limitations in terms of their charging capability. So I hope that kind of answers the question. I think if I've interpreted the question correctly, Tor.
Yeah, I think there's one more question I think we should take, which is, where can improvements be made in SMER? You briefly mentioned a sonar localization system. Can you expand on that, please?
Yes. So in terms of the portable side scan sonar, one of the things that we did attempt to do was actually, look at how useful the portable side scan sonar would to do a larger surveillance of the immediate area, and it can do that. But I think, and I'm not a mine hunter operator, so I'm well beyond my field. But I think in order to do that sort of surveillance, there are better assets. So certainly the portable side scan sonar is one tool that can improve submarine rescue operations. Without a doubt, another would be, and again, it's arguable, but certainly from my personal opinion, is that one of the most precarious parts about a submarine rescue operation is in fact that air-water interface when you're actually launching the submersible itself. And I won't bore you with details of an incident and occurrence that occurred last year, but simply put, if you are able to actually deploy the submersible in any sort of sea state and assure that it's able to therefore be placed in the water safely and then allowed to then submerge safely away from the mothership in a very controlled fashion, and therefore negating, if you like, much of the sea state's impact on the operation, then that would be a major improvement. Now, there are systems out there that have that ability by rigidly holding on to the submersible until it actually goes through that air-water interface. But that's another technical evolution, I think, that could bear some more thinking and some more investigation to just enhance and therefore speed up the process.
Well, I think also there is another part to that question, which is some sort of beacon fitted to the submarine. And I understand that there's such an idea is under development. Australia also has the capability, should it choose to use it, to use spread spectrum, say that when you've had a second whiskey, acoustic signalling to radiate information from the submarine, which helps the search process.
Well, thank you all those who have attended, and thank you for your various questions. We didn't get to all of them, but I'll take those on notice, and we'll certainly put that to the panel separately. And hopefully we'll get back to you with the generic answers to everybody in the future. If you want any more information about our organisations, on the screen there is the Submarine Institute of Australia's website and the Friends of Holbrook Submarines website addresses. Post the webinar, we're going to be sending you a short questionnaire, and also in there you can submit any additional questions that you may have or that come to mind in the next day or two. We'll try and get back to you with those, to all those who've attended this evening with those answers. So thank you once again for your attendance tonight. We hope that you enjoyed the webinar and gained some information out of it. And we certainly look forward to welcoming you back to any future webinars that we hold. So thank you once again, and good night to Australia and good morning to all of you over in the UK.